So having looked at the longest common subword and subsequence problem, we now look at a closely related problem called edit distance. So the aim is to measure how similar two pieces of text are, the so-called document similarity problem. So let's look at the following two sentences. The first sentence says, the students were able to appreciate the concept optimal substructure property and its use in designing algorithms. The second sentence says, the lecture taught the students to appreciate how the concept of optimal substructures can be used in designing algorithms. So the third sentence here indicates how one might obtain one of these two from the other. If you have used certain document preparation systems which allow you to track changes, it will typically indicate the changes between one version of a document and another version like this. So here the green indicates letters which have been, so if we call this version 1 and this version 2, then in going from version 1 to version 2, what we have done is we have introduced the letters in green. So we have inserted these characters. We have deleted the letters marked in red with a line through them. Okay, and in this yellow we have replaced, so we have replaced the T by a B and an S by an E. Okay, so we have 28 characters. You can count that there are 28 characters which have been inserted, including spaces and all that. 18 characters have been deleted. Okay, and 2 characters have been substituted. Okay, so now this can be a basis of measuring how close two documents are to each other. Right? So the edit distance is the minimum number of edit operations required to transform one document to another. So we have to define what we mean by an edit operation. So let's just start with very basic operations. Either you can insert a character, or you can delete a character, or you can replace one character by another one in one step. So replacing, of course, could be thought of as deleting and inserting. So that would be a two-step operation. I delete the character and then I insert the character I want. But I'm going to allow changing one letter A by B or S by T as a single operation. Okay. So in our example, we claimed that 28 characters were inserted, 18 were deleted and 2 were substituted. So the total number of changes we made is 48. If the edit distance is supposed to be the minimum number of changes, it can't be more than 48 because we've already shown that it is possible to do it in 48. Perhaps it's possible to do it in a more clever way in less than 48. So the edit distance is at most 48 for the two sentences that we showed earlier. So this distance is also called the Levenshtein distance because it was first proposed by then Soviet, now Russian scientist called Vladimir Levenshtein. And this, like the longest common subsequence problem, is extremely useful in practice. So the first thing is to suggest spelling corrections. Now if somebody types something that is wrong, okay, then a spelling corrector will have to suggest a correct word from the dictionary to replace it. So which word should the spelling corrector choose? So one criterion for choosing is to identify among all the words in the dictionary that are possible, which one is closest to the one that has been typed. Right? So this can be measured in terms of this edit distance, and then the menu will pop up saying, did you mean to type this? This also happens when you type queries in search engines. Right? So if you type something to Google, Google will sometimes change your query to a word which is meaningful because it recognizes that you have mistyped a name or a concept. We also said that the longest common subsequence problem that we saw earlier is useful in genetics and in bioinformatics. And in the same way, edit distance also, if we want to compare the genetic information in two different species, then it's natural to compare them in terms of the content of the DNA, and DNA are just long strings. Right? So we want to find out how easy or difficult it is to transform one piece of DNA into another, and depending on that, we can tell whether two species are close to each other or not. So if you go back to the longest common subsequence problem, right? So one way of thinking of longest common subsequence is, supposing I just delete all the parts which are not part of the LCS, right? So I had things like bisect and secret. Okay. So now in this, if I deleted the B and the I from here and the R and the E from here, then I'm left with exactly the longest common subsequence. Okay. The other way of thinking about it is that I start with one word and I'm transforming it to this word. So I first delete the B and I, and then I insert here the R and E. right? So I don't operate on both words and delete from both. I operate only on the first word. So I delete the words I don't do, delete the letters I don't want because they're not there in the second word, and I insert the letters that I do want, which are there in the second, not the first. This way I transform the first word to the second word, and this is equivalent to deleting from both and coming to a common subsequence, right? So this tells us that LCS is somehow equivalent to computing the edit distance if I only allow delete and insert, right? So the interesting thing about edit distance is that it also allows a substitution of one character or another. So it might give us a slightly different metric from longest common subsequence. So going back to longest common subsequence, right? It said that if two letters match at the beginning of a word, then it's useful to assume that the common subsequence includes that. So I have this one which says that AI is equal to BJ, so I include this in my subsequence and then I solve the rest of the problem. Otherwise, I take the max of the two subproblems that I get by dropping AI or BJ. Now in the edit distance problem, we have a similar criterion. Okay? If AI is equal to BJ, then I have nothing to do. Right? So the edit distance of words starting at I and j is the same as the edit distance starting at I plus 1, j plus 1. Recall that we are now doing the opposite of longest common subsequence. We are now trying to minimize the number of changes, not maximize the number of matches. So if we see that something is already matched, then no change is needed. So we just move ahead to the next position. Now, if they don't match, now three things are possible, right? So I have AI plus 1 and so on, and I have BJ plus 1 and so on. So the first thing I can do is I can directly make this into BJ. In which case, I have now made the first letters exactly equal, and so I just need to look at I plus 1, j plus 1. Okay? The other thing which I can do is to remove this AI altogether, right? I just remove this AI. So now this discrepancy is gone, but I am still left with the rest of the problem. So now I have to now see if I plus 1 onwards matches j onwards. And finally, the last thing which I could have done is to introduce that this bj at the beginning. Okay? So now this means that these two things now match up. So now I have to look at ai onwards and bj plus 1 onwards. Right? And whichever of these three requires the minimum work overall is the one I want. So I want to take 1 plus the solution for I plus 1 j plus 1, or 1 plus solution for I plus 1 j, or 1 plus solution for I j plus 1, and take the minimum of these three. Right? So this gives us the final inductive structure that we want. So ED, the edit distance for the word starting at I and j, if AI is equal to bj, it is ED of I plus 1 j plus 1. If it is not equal, then it is 1 plus the minimum of the edit distance of these three different subproblems. Okay, and as usual, we extend this to m plus 1, n plus 1, but the interpretation is now different. If one of the words is empty, then the number of changes I need to make is to transform everything else or insert everything from that word here. So if I am looking at bj plus 1 to bn, and on this side I have nothing, then what is the edit distance? Well, I have to basically insert this many letters. How many letters are there? N minus j plus 1. Okay, so the edit distance when u is empty and v is at position j is n minus j plus 1. Likewise, when v is empty and u is not, it's m minus I plus 1. Okay, because I have to insert all those letters. So this is a slight difference. It's not 0, but it's the cost of using up the letters which are there, which are missing in this word. So the inductive substructure in edit distance is exactly the same as in LCS. Okay. Every position depends on I plus 1 j plus 1 and the I plus 1 j and ij plus 1. Okay. So we have the same three neighbor dependency that we had as we did before. And as usual, we can start at the bottom right corner and work backwards row by row or column by column. Okay. So in this case, remember that the boundary condition is not 0, but it is n minus j plus 1. So as I go up, the number increases. Okay. So this is my boundary. And now I can just apply my recursive thing which says that, okay, t matches. So the edit distance at t is 0 because I have nothing to do and there's nothing to do beyond that. Everywhere else, because they don't match, the edit distance is just going to be the minimum of the remaining 3, right? So it's the minimum of the remaining 3 plus 1. So in this case, if I look at this, for example, the minimum of 0, 1 and 2 is 0, plus 1 is 1. Okay, the minimum of 4, 2 and 3 is 2, plus 1 is 3, and so on. Okay? So it's a minimum of those plus 1 to make the current change. So I keep doing this, and as I go left, okay, eventually I will find that the minimum edit distance between bisect and secret is actually 4. I need to make 4 changes. Okay, just using the inductive definition that we had done earlier. And as before, now the question is, how do I recover the solution from this? So I follow the path. Right? So why did I get a 4 there? Because it is the minimum of its 3 neighbors. B is not equal to S. What is the minimum of these 3? It's 3. So I went down. Similarly, why is this 3 here? Because it's the minimum of these, so I went down. So every time I go down, okay, it amounts to saying that I go from ij to I plus 1j. Right? And if you remember, in our case, I plus 1j and ij is corresponds to deleting. Similarly, at this place I go right. Right? This means I go from ij to ij plus 1. This corresponds to inserting. So what I can read off from here is that when I'm going, I delete this b, I delete this I, then I come here, I insert this r, and I insert this e. And these are exactly the 4 changes that I need to make in order to transform bisect into secret. So the pseudocode for edit distance is very similar to the longest common subsequence. The only major change, one is in the initialization. The values of the boundary are not 0, but whatever is required to complete the editing. Then as usual, I start at the bottom right and I do columns from right to left, rows from bottom to top. If the current value, if the 2 values that I'm looking at, u of r and v of c, are the same, then I just postpone the edit distance to the next thing. I have nothing to do here. Otherwise, I take the minimum of the subproblems and I add 1 for the current change. And finally, I return the value at 0, 0. The complexity is order m times n. It's exactly the same as the previous one because I have to fill up this table of size m times n and it takes a constant time to compute. Now in all these 3 problems, there's another issue which we have not addressed, so let's deal with it now. So there's the notion of space complexity. So we have this table that we have to compute, which we have agreed is m times n. But notice that the way we computed it, for example, was to compute this column, then this column, then this column, and so on. Right? So at any given point, when I'm computing the second column, for example, I only need the first column. Now, when I reach the third column, okay, this column is now not needed anymore because the third column depends only on the second column from the right. So if I fill column by column, I only need the next column, the column on my right, and the current column. Okay, or if I'm doing it row by row, the next row and the current row. So in other words, by just keeping 2 columns or 2 rows, I can completely compute this thing back to 0, 0. So therefore, there's actually no need to do m times n size table as storage. I still have to compute m times n. So the time complexity remains m times n. Okay, so time is m times n. What we're saying is the space can be reduced if, let's say, that n is the smaller of the 2. The space can be reduced to order n, okay, by just keeping 2 columns. Okay. And now you might ask, how do I recover the solution? Because in the solution I trace back the path and the whole thing. Well, you can actually keep track incrementally as you are going. You can build up the solution associated with each entry incrementally. So even that can be done in order n space. So you don't need this table at all even to compute back the witness for the given numerical solution, right? So in all these problems where we have a very limited neighborhood dependency in our dynamic programming, you can actually often make do with much less space than it seems to require in terms of the actual table as given to you.